Okay, an acid is a substance which, when dissolved in water, will produce hydrogen ions as the only positive ions. We have two types of ions: the positive ions, which are the cations, and the negative ions, which are the anions. So if you dissolve a substance in water and when tested, it's found that the only positive ions present in that solution is hydrogen, then that substance is an acid. Alright, although we agree that all acids have hydrogen ions in them, it's also been observed or discovered that not all the hydrogen, in some acids when dissolved in water, they don't dissolve all their hydrogen ions into that water. When this happens, we say the substance is not capable of ionizing, releasing the hydrogen it has, or dissociating into hydrogen ions. So when this happens, we call those kind of acids that do not ionize, that do not release all of their hydrogen into the water, we call those kind of acids weak acids. So when we say weak acids, we mean that they are acids which, when dissolved in water, though they will dissolve their hydrogen ion into the water, but not all of the hydrogen ions will be dissolved into water. So example of weak acids are hydrogen fluoride, acetic acid, ethanoic acid, or in general all the natural acids, that is organic acids, acids found in plants. Those are organic acids, those are natural acids. All the natural acids, all the organic acids are mostly weak acids. But then other acids, artificial acids, the ones that are prepared in the laboratory, are strong acids, which tells you that they will completely dissociate their hydrogen ions when dissolved in water. Okay, so we move to physical properties of acids. That's how do we know acids? How do we identify them when we see them? Now, dilute acids have a sour taste. You know how things get sour, and when you taste them, you get slapped. Let's use that term now. Now, if you eat unripe fruits, you eat unripe pawpaw, unripe mango, you would observe some slap, so to say. Now, that's because of the acids found in them. So you may be thinking, how did they test them to know acids, dilute acids have sour taste? Did they take in acid, drinking acid? No. If you test, since we said organic acids found in plants are organic, so they are still acids. So now these acids have sour taste. And number two, we said acids turn blue litmus red. For those of you that have not seen litmus paper yet, you will see when we resume fully. But if you take a blue litmus paper and dip it into a solution which is an acid, then that blue litmus paper will turn red. Also, number three, the concentrated forms of strong acids like hydrochloric acid, sulfuric acid, etc. are corrosive. Being corrosive means it can cause corrosion. It can cause your metals to rust. So it can attack metals. So those are the physical properties of acids. And when we talk about the chemical properties, we said number one, acids react with some metals like zinc, iron, and magnesium to liberate hydrogen gas. So when zinc comes into a solution where an acid is present in that solution, the zinc will displace the hydrogen. What does it mean? Zinc metal will come into the solution and will liberate, like pursue hydrogen. Let's say that pursue hydrogen. So hydrogen will leave and zinc will take that place. That's what we mean by replace or displace the hydrogen ions in that acid. So that's the first chemical property of acid here. Number two, acids react with insoluble bases and alkalis. What's the difference between base and alkali? When we get to base in our next class, we'll discuss that. But in a brief way, a base is the opposite of an acid. So a base is a substance which, when dissolved in water, will produce OH ions. But let's not go there. Now, an alkali is still a base, but a base which can dissolve in water, which means not all bases can dissolve in water. Now, the ones that can dissolve in water are the ones we call alkalis. So number 2, we say acids react with insoluble bases and alkalis to form salts and water as the only product. So acids will react with a base to form salt and water. Number 3, we say acids react with trioxocarbonates 4 to liberate carbon 4 oxide. So when you add acid to any trioxocarbonate 4, like say we add hydrochloric acid to sodium trioxocarbonate 4, you will have the trioxocarbonates will liberate carbon 4 oxide. And that is all for physical and chemical properties of acids. Okay, so how do you prepare acids? That means you can prepare acids in the laboratory. Now, how do you do that? Number 1, by the reaction between an acidic oxide of a non-metal, take notes, and water. So if you react an acidic oxide, an acidic anhydride, if you dissolve that with water, then you're going to form an acid. Take for instance, you dissolve SO2, which is a gas, in water. SO2 is an acidic oxide. The O2 here makes it an oxide, so sulfur oxide. Now, when you dissolve that in water, then you will be forming an acid, H2SO4, which we call sulfuric acid. So you can react an acidic oxide with a non-metal, an acidic oxide of a non-metal with water to have an acid. Now, this is the general way of preparing acids. It's the most general, in case it comes in your exams. What is the general way of preparing acids? It's always the reaction between acidic oxide and a non-metal. Now, number 2, displacement of a weaker or more volatile acid from its salts. When you say volatile, means how easy is it to evaporate, catch fire, something like that. So it can displacement of a weaker, we said something about displacement, replacement, displacement. So displacement of a weaker or more volatile acid from its salts. So if you carry sodium chloride, which is a salt, and add to sulfuric acid, what do you think will happen? Now, the weaker or more volatile acid will be displaced by a stronger or less volatile acid, and so a reaction will be formed. Sodium chloride plus H2SO4, which is sulfuric acid, will produce NaHSO4 and HCl, which is hydrochloric acid. So you've prepared hydrochloric acid from sodium chloride and sulfuric acid. Now, number 3, we say direct combination of constituent elements is what we call synthetic method. Direct combination of constituent elements. How do you cook your soup? You add salt, add Maggi, add the other ingredients, but what are you doing? You are adding this plus this plus this, and at the end of the day, when you finish adding, you come out with a delicious meal. You eat your soup. Now, we can prepare acids like that. If we say we want to form hydrochloric acid, what are the elements in hydrochloric acid? Hydrogen and chlorine. Okay, just like we prepare our soups, we can bring hydrogen, add to chlorine, right? And then we form hydrochloric acid. So that's another method of preparing acid, direct combination of the constituent elements. Alright, we get to uses of acids, which is the last thing we're going to consider today for SS1. In case you're already thinking bad about acids, since we say it has sour taste, sorry, which means it doesn't allow you eat your fruits. You have to wait until it's ripe though. And in case you're thinking bad about acids, then you should know it has uses too. I mean, your sicknesses, ailments, diseases, all those things that happen to human beings to make them fall ill, they are not strong anymore. Those things are harsh already. And so you need harsh chemicals to attack harsh things. So, number one, use of acids. Acids are extremely useful chemicals in industries to make fertilizers, detergents, and what? Drugs. So in the fertilizer industry, acids are used. I hope you've heard of, you've seen some fertilizers. And if you've not seen, you've seen detergents at least. Do you eat them? No, because it's dangerous. It contains acids. You've seen drugs. Now, these ones are, prepared in a safe way, that they're not harsh amounts of these acids, but enough amounts to take care of the sicknesses. And now number two, they are used in industrial processes as drying agents, oxidizing agents, and catalysts. Now, when you get to SS2, you'll be taught oxidizing and reducing agents. You would know more about oxidizing agents. But as drying agents, we know if you visit the villages, you see the old women, how they protect their fishes. They use salting method. They apply salt to the fish, and the fish is safe. What is the oil or the salt doing? The salt serves as a drying agent. Also, it's a preservative though. But now look, salt has the ability to drag out. It absorbs water. So if you place it on a watery surface, it will draw the water to itself. So the fish now becomes dry and the salt is watery. So that's a drying agent and also a catalyst. You learn about catalysts in SS2. Now number three, hydrochloric acid can be used to remove rust. Remember we said harsh acids can be corrosive, means they can cause your metals to rust. But here is another acid where you can use to remove rust caused by an acid. So it's also useful in removing rust. Alright, so that will be all for today in SS1. Hope you enjoyed the lessons. We'll come back next week. We'll be dealing on bases and alkalis. Bases and alkalis. And do well to copy all the notes I've posted. I've posted 4 pages of my notes. I label them 1, 2, 3, and 4. Copy them accordingly. I will ask for it. Alright, if you have any question, feel free to drop on the group and I will answer your questions. Thank you and have a great day. Okay, so today we'll consider bases and alkalis. Base and alkali. Last time I said there is no big difference between a base and an alkali. So when we say base and alkali, we're almost saying the same thing, only that not all bases can dissolve in water. So the ones that can dissolve in water are the ones we call alkali. So generally they are all bases. Okay, so a base is a substance that produces hydroxide ions, that's OH minus, when dissolved in water. Remember we said an acid is a substance which when dissolved in water produces what? Hydrogen ions, that's H plus ions. Now, we said the base is the opposite of acid. So a base is a substance that produces not hydrogen now, hydroxide ions, OH minus, that's hydroxide ion, when dissolved in water. That means if you dissolve a substance in water and then when tested, you find that the only positive ions found in that substance is hydrogen ions. What do we say that substance is? Good, an acid. But if when dissolved in water, you find OH ions when tested, that's hydroxide ions, then what do you say that substance is? That substance is a base. So if we say that bases contain hydroxide ions, that's OH minus. Therefore means that most hydroxides and most oxides of metals are all bases. Take note, not all, but most of them, since they contain hydroxides and oxides, they are bases. Okay, so remember when we said that acids turn blue litmus paper red? Well, a base can also have an effect. It means can also change the color of litmus paper. So since acids turn blue litmus paper red, a base or an alkali would turn red litmus paper blue. So you agree with me that base is the opposite of acid. Now I need you to focus, just listen. Think about this. If we say, okay, we call sugar, or let's say very sugary drink, juice, sweet, and we call it acid. And let's call bitter leaf juice, when you squeeze out the liquid in bitter leaf, and someone says drink it. Now let's keep those two liquids opposite, and then we call the sweet one acid and we call the bitter one what? Base. Now I want you to think, if we carry the orange juice or whatever sweet juice it is, and we keep pouring it into the bitter juice, keep pouring it, just keep pouring it as long as the container is not filled. Well, if it's filled, we turn it into a bigger container. What are we trying to achieve? We want to see if we can make that bitter juice sweet. What do you think will happen? We'll have to add and add, but one day that juice will not become the bitter leaf juice, so to say, will not be as bitter as it was at the beginning, and at some point it will become not bitter anymore. Now at that point where the bitter leaf juice is no more bitter, we would say neutralization has taken place. So you can drink it without squeezing your face anymore. So what am I trying to say? Neutralization can happen between acids and base. In fact, that's what we do in the labs. That's one of the first practicals you'll be handling as SS1, where acids will be mixed with a base. I'm using the word mix now because you don't know how it happens, but you will see that in the lab when we resume. Acids are mixed with bases so that you neutralize the power of the acid and also neutralize the base, so everything becomes neutral, such to say like water is neutral. So neutralization can happen between acids and bases. So if an acid is gradually added to an alkali, remember we are calling this one alkali because it's in water and we need something that can dissolve in water, so we cannot say base. It's also a base, but remember bases that are soluble in water are called alkali. So if acids are gradually added to alkalis, then there will come a stage when the solution becomes neutral to litmus. Remember, acids turn blue litmus red, and bases or alkalis turn red litmus blue. Now if we are mixing the two together, mix it to a point that it's neutral, what will happen to litmus paper? Will the mixture turn litmus paper blue? No, because it's no more an acid. And it won't turn blue litmus red because it's no more a base. It's neutral. So you put in a blue litmus paper into it, it comes out blue. You put in a red litmus paper into it, it comes out red. And you say, okay, this solution is neutral. And you say the process is called neutralization. Now, generally, when acids react with a base, when an acid reacts with a base, just like I've explained, there are only two products you should expect: a salt and a water. Now, when we're saying salt, don't think of the table salt, like the small, the white salt, That's a salt actually, but that's a common salt. Salts that are formed in acid-base reactions and not the ones you use in your houses. So, but these two products must be formed. So we say acids and bases react with one another to yield two products. How many products? How many products? Two. What are the products? Water and a salt. Now, this is the reaction that is called neutralization reaction. Like in your notes, you see there, hydrochloric acid was reacted with sodium hydroxide, and what was formed? NaCl, sodium chloride, which is a salt, plus what? H2O, which is water. So you agree with me that acids will always react with base to form salt and water only. So if we say that a base when added to an acid can neutralize an acid, then we can also define a base as a substance which will neutralize an acid to yield salt and water. You understand? Good. So now, if we see a substance, how do we know if it's an alkali? Physical properties of alkalis. Number one, alkalis have a bitter taste. Yes. If you take it to your tongue, don't do that. It should taste bitter. So if it accidentally spills into your tongue or to your mouth and it tastes bitter, that's a base, but don't swallow it. So alkalis have a bitter taste. Number two, alkalis are soapy to the touch. That means if you touch it, if you dip your hand into an alkali and you sort of rub that two fingers together, it should feel soapy, like you put your hand into soap. It feels slippery. So alkalis are soapy or slippery to the touch. Number three, alkalis turn red litmus blue. So the opposite of acid. Acid turns blue litmus red. So alkalis turn red litmus paper blue. Number four, concentrated forms of caustic alkalis are corrosive. Remember, concentrated forms of acids are also corrosive. So base here, when it's very concentrated, when it's concentrated, then it can also cause corrosion. And under chemical properties, we see that all bases react with acids to form salts and water. We have explained that. And then an interesting one, number two, alkalis react with ammonium salts in the presence of heat. That's heat is applied to generate ammonia gas. So ammonia gas can be prepared using this method. Now, this is a simple test for alkali. This is how we can carry out a simple test to know if this compound is an alkali, if it contains an alkali, and so on. Okay, now for the uses of alkalis. Number one, sodium hydroxide. Remember that sodium hydroxide contains hydroxide ion, like we said, hydroxide. We said bases must contain hydroxide ion. So sodium hydroxide is used in the manufacture of soap. If you visit people that manufacture soap locally, you would see that they use sodium hydroxide. Also, apart from manufacturing soap, also sodium salts and also plastics are made from sodium hydroxide. Not just that all plastics are made from sodium hydroxide, but sodium hydroxide can be used to make plastics. And it's also used to refine petrol. You understand that when you get to SS3 and you're doing cracking. Number two, potassium hydroxide is used in the manufacture of liquid soap. I'm sure you all know liquid soaps. Now, potassium hydroxide can be used to manufacture liquid soap. Also, number three, calcium hydroxide. Remember, we're talking about hydroxide. Hydroxide, that means it's a base. Calcium hydroxide is used in the manufacture of mortar. When we say mortar here, it's not the mortar and piston in your house that you use in pounding pepper or crayfish or whatever. Now, mortar here is used by bricklayers. You know what we call plaster? So you want to plaster your wall after laying the block. That plaster, that thing you call plaster, is mortar. Mortar is just a mixture of cement, sand, and water. No gravel, nothing like stones. So mixture of cement, sand is called mortar. So calcium hydroxide is used in the manufacture of mortar, cement, and plaster. It is also used to neutralize acid soils. Remember, we said that base, when added to an acid, can neutralize that acid. Well, if a soil is acidic, means when your soil is acidic, it can't grow plants well. The acid content in the soil can disturb the growth of plants and all that. Just like we have in acidic water, we can have water that is too acidic. So people that rear fishes, if they use that kind of water to rear their fishes, then that water can kill those fishes because they drink it, they use it. So those kind of acidic soils can be neutralized using a base, since acids are neutralized by bases. Now, calcium hydroxide can be used to neutralize those kind of acidic soils. Also, magnesium hydroxide is also used in the manufacture of toothpaste. Most of you are not good at reading labels. If you carry your toothpaste, look through it, you will see the different things used in producing toothpaste. And some toothpastes can be stated out there well cleared, and magnesium hydroxide can also be used in the manufacture of toothpaste. Number 5, aqueous ammonia. What is aqueous? Remember, I told you in class last time that an aqueous solution is a solution where water is the solvent. So when you are dissolving something in water, not oil, not cream, not something else, but water, as long as it's water, then you call that an aqueous solution. So if you dissolve ammonia in water, that becomes aqueous ammonia. Aqueous ammonia is used for bleaching cloth, and also as a detergent. Now, some people sat down and did some tests to come out with these definitions of acid and base we have. So we're going to look at these people. First one is Arrhenius. We've heard of Arrhenius in SS1, in first term. So Arrhenius' concept of acid and base. Now, Arrhenius defined acid as a substance which, on dissolving in water, dissociates to produce hydrogen ions as the only positive ions. And that's not far from our definition of acid. Now, take for instance, HCl is an acid. When dissolved in water, it should dissociate to form H plus and Cl minus. And that's among those ions, the only positive one is H plus. So that's the definition of acid according to Arrhenius. Now we said a base is a substance which combines with H plus ions to form water. So while acids will form that H plus, a base should combine with that H plus to form water. Look at in the equation down there, CuO plus 2H in a reversible reaction formed Cu2 plus water H2O. So if you look at the left hand side of the equation, the O from the CuO combined with the H from this 2H combined with the two hydrogens to produce at the other end of the equation H2O. So according to Arrhenius' concept of acid and base, that is a base. Now getting to Bronsted-Lowry concept of acid and base. Now take note of this. Bronsted-Lowry is not one name. Bronsted is someone, Lowry is someone else. So I would say Mr. Bronsted and Mr. Lowry shared combine their ideas to form this. So Bronsted and Lowry concept of acid and base. Now they say that acid is a substance which will donate protons to a base. Now remember, in our definition of acid and base, we said that acid is a substance which produces hydrogen ions or protons. So we can call hydrogen ions protons. So Bronsted and Lowry, they're dealing with protons instead of calling it hydrogen ions. So whenever we're talking of Bronsted and Lowry concept of acid and base, we'll be talking of protons and not hydrogen ions, but they are the same thing. Now, according to Bronsted and Lowry, acids are proton donors. They donate protons. Acid will donate protons, that's give out protons to a base. And he said a base is a substance which will accept protons from an acid. So when an acid donates the proton, gives out the proton, a base, on the other hand, should accept the protons. You understand? So according to Bronsted and Lowry, an acid is a proton donor, proton giver, hydrogen giver, while a base is a proton acceptor. Now listen very clearly. We said that if we dissociate, if we dissolve hydrochloric acid HCl into water, then hydrochloric acid should dissociate into H plus and Cl ions. Dissociate these ions. Now HCl has how many elements? 2 elements, H and Cl, hydrogen and chlorine. Now remember, in Bronsted and Lowry version of acid and base, we'll be calling that H plus proton. So whenever you see H, according to Bronsted and Lowry, call it proton, just under this Bronsted and Lowry definition. So now we'll say, how many protons does HCl have? Since it has only one H, it means it has only one proton. And now Bronsted and Lowry version says that an acid is a proton donor. It gives out protons to a base. Now in that equation, HCl, when dissolved in water, should donate its one proton. The H there is the proton. Should donate that proton to a base. So I'll ask you now, if HCl donates one proton, how many H will be left there? Good. No H anymore, because just one H was there, just one proton was there. So that one proton, that one hydrogen has been donated to a base. And take note, in Bronsted and Lowry version of acid and base, base is not the substance which when dissolved in water would produce OH ions. No, it is the one that accepts the electron. So the one that has the negative sign is the base. So in HCl, Cl is the base, right? Good. Now H, when donated, when given out, has lost one proton, has donated one proton. Now according to Bronsted and Lowry version of acid and base, when H donates that proton, what is left behind is called conjugate of that other that is donated. So in HCl, when H is donated out, what is left behind is what? Cl. So Cl becomes a conjugate of H. And since Cl is the base, it's base because it's the one accepting the electron now, Cl becomes a conjugate base. So in that note, you see a conjugate base is formed when an acid loses one proton. So you see HCl lost one proton, H was lost on the other side of the equation, and what was left? Cl minus. So Cl is the conjugate base of HCl. So that means that the difference between an acid and its conjugate base is one proton. I'm trying to say that an acid and its conjugate base differ by only one proton. And you can turn it the other way around, that the difference between a base and its conjugate acid is 1 proton. So therefore, a base and its conjugate acid differ by how many protons? 1 proton. Good. Now, if you look at that table below, you see acid and conjugate base. Now, we see the first acid is sulfuric acid, H2SO4. If you look below, when H2SO4 lost 1 proton, means lost 1 hydrogen, what was left behind is HSO4. Remember, H was 2, so H now becomes 1, because 1 H has been lost, 1 proton has been given out, so it becomes HSO4. That HSO4 is the conjugate base. Take note, you see a minus, 1 minus in the conjugate base of H2SO4. That's because 1 H has been lost, so you see 1 minus there. Look at the second one. HSO4 lost 1 hydrogen too. When it lost that 1 hydrogen, that means it donated the proton. And now, since 1 hydrogen, 1 proton has been lost, what is left behind, which is SO4, is the conjugate base. And remember, the first equation was H2SO4. It has lost these 2 hydrogens, these 2 protons, so 2 minus on top. The same way, HCl, when it loses 1 proton, loses 1 hydrogen, then what is left behind is Cl. That 1 hydrogen makes the Cl negative because it has lost it. Same thing with HNO3, it becomes NO3, it has lost 1 hydrogen. H3O, remember in our first class, hydroxonium, lost 1 H, that's donated 1 H, donated 1 proton, and became H2O. Same thing, NH4, when it loses 1 H, becomes what? NH3. So you understand Bronsted and Lowry concept of acid and base. Now, we also said that a base can have a conjugate acid. So, and a base will be accepting. Remember, acids donate, they give out. So base will accept. So when we're talking about base and its conjugate acid, the base was H2O in that table where we have base and conjugate acid. The base is H2O, that's water. Now, when it gained 1 proton, sorry if I may be saying electron instead of proton, please take note, it's proton. H there is proton. Now, when it gained 1 H, 1 proton, it becomes H3, not H2 anymore, H3O. So that H3O is the conjugate acid. Please take note to study this thing well, so that you'll not be confusing yourself with conjugate base and conjugate acid. But the whole summary of this conjugate thing is that when an acid or a base is dissolved in water, if the acid donates a proton, what is left behind is the conjugate base of that acid. And if the base, when the base accepts the electron, what is formed is the conjugate acid. You understand? Now, the Lewis theory of acids is there for you to read. It's quite simple. A Lewis acid is a substance which can accept a pair of electrons. Now, this is dealing with electrons, not protons now. So, Lewis theory of acid deals with electrons. Bronsted and Lowry theory of acid deals with protons. Alright, so if you read clearly, you will understand. But take note, Lewis acid is electrophilic, while Lewis base is nucleophilic. Alright, now that we know what an acid is, and we also know what a base is, it's left for us to figure out, how do we know the amount of acid contained in a solution or the amount of base contained in a solution? What I'm saying is, how do we know how acidic a solution is or how basic it is? Remember, when I say how basic, it means the amount of base, amount of alkali. So I say how acidic a solution is or how alkaline a solution is. Now, we're going to take this measurement using what is called a pH scale. pH is a short form for potential of hydrogen. So we're looking at pH scale. Now pH can be defined as a measure of the acidity or alkalinity of a solution. It's a measure of how acidic or how alkaline a solution is. We can also say it is a measure of the hydrogen ion concentration in a solution, or the hydroxide ion concentration in a solution. And the formula for pH is minus log to base 10 of the hydrogen ion concentration. That is pH equal to minus log, open a bracket, H plus, close the bracket. If you want to interpret what you just wrote, you're saying pH equals to minus log to base 10 of the hydrogen ion concentration. Okay, now the concentration of hydroxide ions in a solution is always inversely proportional to that of the hydrogen ion concentration. Because of this, the pH value of that solution would indicate both the acidity and the alkalinity of that solution. Now, if you go down that note and look at the pH scale there, it's labeled 0 to 14, where 0 is strongly acidic, 7 is the center neutral, and 14 is strongly alkaline. Now, that means the scale ends at 14. So it means if you add up the hydrogen ion concentration and the hydroxide ion concentration, everything should equal 14. Now, that being said, it means if you want to find the potential of only hydrogen ion concentration, you have to subtract that of hydroxide from 14, since 14 is the highest. So therefore we can say that pH plus POH, that's pH is potential of hydrogen, POH is potential of hydroxide. So we can say the hydrogen ion concentration plus the hydroxide ion concentration equal to 14. You understand? That's why you have in your notes pH plus POH equal to 14. Now, to find POH, you say 14 minus pH to get your POH. So remember, the formula for pH is minus log of the hydrogen ion concentration. That's minus log H plus. Then also remember that pH plus POH equals 14. Now, back to the pH scale. If you carry a test on a solution and the pH value reads, look at your scale, it reads 1 or 2 or 3, it means that that solution is acidic. Look at your arrow down on that scale. From 0 till 7, where you have neutrality, is increasing acidity. So if the scale shows 0, it means it's very acidic, strongly acidic. It shows 1, okay, it's less acidic than 0. Shows 2, it's still acidic but less acidic than 1. Shows 3, then it's less acidic than 2. So if it gets to 6, it's less acidic than 5. But at 3, 4, 5, or 4, 5, 6, it's not as strongly acidic as 0 and 1. You understand what I'm saying? Now, when it gets to 7, if the scale reaches 7, that solution is not acidic, it's neutral. That's where your water is. So water you drink is not acidic, it's not basic, it's not alkaline. So if you drink that water, then it's not bad for consumption. But if you taste water, if you carry out tests on water, pH scale, pH test on water, and you discover that water does not read 7, then that water has a problem. So if the pH scale reads above 7, say 8, 9, 10, now it has crossed the neutrality sign. From 0 to 6 is acidic. Then 7 is neutral. From 8 to 14 is alkaline. So if a solution reads 8 or 9 or 10 or 11 or 12 or 13 or 14, that solution is alkaline. So now listen, a high pH value, when we say high pH value, we're talking about pH value of 12, 13, 14. So a pH value with that number, a high pH value like that, indicates that that solution has a low hydrogen ion concentration. That means it doesn't contain acids much. So low hydrogen ion concentration means it's weak. It's a weak acid. I mean, it's alkaline. Good. It's alkaline, and therefore means that it's strongly alkaline and weakly acid. You understand? Let's put it that way. But if you're if you have a low pH value, say 0, 1, 2, 3, 4, 5, 6, then that solution is acidic. And then since it's acidic, we say it's strongly acidic and weak alkali. You understand? All right. So at neutrality, the neutral pH value is 7. What does that mean? That for you to have a neutral substance, a neutral solution, neutral means it's not acidic, it's not alkaline, then your pH scale should read 7 when tested. Good. So since we said that the total concentration when we add acidic concentration and alkaline concentration should be 14, then for them to be equal, for both to be equal, then it has to be neutral, right? So H plus, for H plus to be equal to OH minus, they both have to be at 7. That's why I see H plus equal to OH minus equal to 10 raised to power 7. 10 raised to power 7 minus, if you want to calculate that, minus log to base 10 of the concentration there. Alright, so now let's see some calculations. Example 1 says, calculate the pH of 0.005 mole dm cube tetraoxosulfate 6. So this question has given us the concentration of tetraoxosulfate 6 as 0.005, and the question says, what's the pH of that solution? Alright, in order to solve this question, first of all, we have to break down the tetraoxosulfate 6, the equation you are seeing there. You have to break it down to see how many hydrogen ions do we have there. That means, what's the hydrogen ion concentration in tetraoxosulfate 6? And once we do that, we discover that it's just 2 hydrogen ions. So we say H plus ion concentration equals to 2. Now, since it's 2 and the concentration of tetraoxosulfate 6, H2SO4, is 0.005, then the hydrogen ion concentration is going to be 2 times the total concentration of the tetraoxosulfate 6 in the solution. You understand? So we have the 2 times 0.005 to get only the hydrogen ion concentration, which is what? 0.01 in your standard form. You remember your mathematics standard form. 0.001. 0.01 is also written 1 times 10 raised to power minus 2. Okay? Okay. Now, having gotten the pH of the solution, I mean the hydrogen ion concentration of the solution, we can use that to calculate the pH of that solution. If you look down, remember the formula for pH. pH equals to minus log to base 10 of the hydrogen ion concentration. Good. We've gotten a hydrogen ion concentration. So we just put it in there in the equation. So it becomes minus log to base 10 of, what's the hydrogen ion concentration? 0.01. So if you punch your calculator, you come out with the answer 2. Now, going back to your scale, if you look down, you see 0, 1, 2. So it means after everything, that's where the test, that after the test, that's our pH measure. It reads 2. Now, class, tell me, since it reads 2, is the solution acidic or alkaline? Good. That solution is acidic and even strongly acidic. So the pH of 0.005 mole dm cube tetraoxosulfate 6 is a strong acid. Okay, so we look at the second question. Look carefully now. This one is not like the first one. A sample of orange juice is found to have a pH of 3.80. So this one, the pH is already solved for us. pH of 3.80. What is the concentration of the hydroxide ion in the juice? This time, we're not looking for the pH. We're not looking for the potential of hydrogen, because we've been given. We're looking for the potential of hydroxide. So this question already tells you that the answer you should get should be above 7. That is because you're looking for the potential of hydroxide. That is, the solution is expected to be alkaline. And being alkaline, that's from 8 to 14. Okay. Now we are given pH value 3.80 and we are asked for pOH value. Now you remember that pH plus pOH should give us 14. So we can deduce that and get our pOH value, right? Now if we do that, pOH will become 14 minus pH. So if we put that in our equation, in our calculators, 14 minus 3.8, which is a pH, will give us pOH value of what? 10.2. So we see the pOH value is greater than 7. It's 10.2. Now that's not where you stop. Remember that pH equal to minus log to base 10 of hydrogen ion concentration. The same way, pOH will be equal to minus log to base 10 of hydroxide ion concentration. So the difference is just the H plus has changed to OH minus now. Now we've now gotten our OH value, pOH value, which is what? 10.2. I'm going to just fix it into that our equation. So pOH equals to minus log of the hydroxide ion concentration. Remember, you've already gotten your pOH value, so directly in the equation, 10.2, which is the pOH, equals to minus log base 10 of OH minus ion concentration, equal to 10.2. It means the same thing. Now if you put it that way, then want to move the minus sign to the other side. So log of OH minus will become what? Minus 10.2. So if you get that line, then OH minus is simply an anti-log of 10.2, which is 1 all over 10 raised to power 10.2, which is equal to 6.3 times 10 raised to power 11. Let me put that in a video so that you understand better. Okay, so we know how we can identify the pH value of a solution. That's how we can know how acidic or how alkaline a solution is using a pH scale. But now, how do we know if we see the reaction physically? That's what I'm saying is, if an acid is turned into a base, how do we see physically and know if the pH of that acid is changing or if the pH of the base is changing? Physical things now, how to see it and say, okay, yes, it's changing without using a scale. Now, there are things we call indicators. Indicators. If you look at your notes, you see indicators. Indicators are weak organic acids, or they are weak organic bases, which will produce different colors in solution according to the hydrogen ion concentration in that solution. So it means if we use an indicator and add it to our solution or one of the reactants, maybe the acid, and then we start putting the base into it, at a point, with the help of the indicator, the solution should change color to tell us, this ion concentration, hydrogen ion concentration in this solution is now no more, it's neutral. You see color changes. That's what we use in titration, which you will be doing in the lab when you resume fully. So indicators, define what indicators are. Now acid-base indicators is general for any kind of test, But let's think of, since you're dealing with acid base now, and we talked about acid last class. When an acid is reacted with a base, we can use these indicators to check the pH value. So acid-base indicators are dyes. You know what a dye is, gotten from pigments of plants. Dyes which change color according to the pH of the medium. Take note, indicators are weak organic acids. Remember we said acids from plants, natural acids, are called organic acids, and that they are generally weak acids. So acid-base indicators are dyes, means a weak acid, which is a weak organic acid or base, which change color according to the pH of the medium. Now, you've heard of litmus paper. Those of you who have not seen it, you will see it as we resume. Litmus is a common indicator which is red in acid and blue in alkali. So if you put blue litmus in an acid, the blue litmus should turn red, and if you put that red litmus in base, the red litmus should turn blue. So that litmus is an indicator. You understand? It's sort of an indicator now. It changes color according to the hydrogen ion concentration of that solution. So litmus paper is the most common, is a common indicator we all know, or we will know if we don't. Now, indicators are used in titration solutions to signal the completion of the acid-base reaction. Remember we said the other time we discussed neutralization. If you keep adding the acid to the base or keep adding the base to the acid, there will come a point where the acid is neutral, no more an acid, no more a base now. So it's neutral, like your water. Remember when we said if you keep adding the sweet juice to your bitter leaf juice, so what happens at a particular time? Neutralization takes place. So indicators can be used in titration. Titration is a neutralization reaction. So in titration, to signal the completion of the acid-base reaction. When acid-base reaction is complete, it means you have attained neutralization. And how do you know that? Indicators should help you know that. Now, if you look at that table, a table of indicator, the color of those indicators when in acid, color of the indicator when in base, and the pH range for the color change. Now, we've already discussed what pH is and all those. So now, all these indicators, you will see some of them in the lab when we resume, so don't be too scared with the names you'll be hearing, but just take note of the colors they have when in base or when in an acid. Number one, they will have methyl orange. It's a very common indicator. If you put it in an acid, it should have a red color, and if you put it in a base, it should have a yellow color. Now, methyl red, if you put it in an acid, it should have a yellow color. If you put it in a base, it should have a red color. Phenol red, if you put it in an acid, the acid should turn to yellow color. The solution should be yellow in color. If you put it in a base, the solution should be red in color. And phenolphthalein, so if you add it to an acid, it doesn't change the color, but there is the phenolphthalein is present in there. What will happen is, during the titration, when it's neutral, when the experiment is neutral, when the whole reaction is neutral, then you will see the color change. But when you just drop it into the acid, there will be no color change. So don't be scared. Don't say you've not dropped enough and you keep dropping. 2 drops is okay, even if it doesn't change color. That's why I've given you this table to know. If you drop phenolphthalein indicator into an acid, the color should not change. But if you drop it into a base, it will change color to pink. And we know how litmus paper does change color. Red in acid, blue in base. Now, if you look down to the bottom of that first table, you will see I'll say go to acid-base titration before the table. That's before this second table you are seeing down here. You should come down to the topic acid-base titration. You understand? If you finish writing acid-base titration, before buffer solution, put in that table of that has strength of reactants, titration reaction, rapid change, and indicator used under it. Now I'll go to acid-base titration. An acid-base titration is an experimental procedure used to determine the unknown concentration of an acid or base by precisely neutralizing that acid or base with an acid or base. So if you are using an acid, you neutralize it with a base. If you are using a base, you neutralize it with an acid of known concentration. And whatever you are using to neutralize the other one, the concentration is known, but the other one, the concentration was not known. You understand? This lets us quantitatively analyze the concentration of the unknown solution. So in acid-base titration, one solution is unknown, in concentration is not known, but the other one is known. You know, in mathematics, we can use the known to find the unknown. So when you finish the whole titration, you use the volume used up in the titration. You will know, you will understand this better when we start the practical. So you will be able to find the unknown concentration of either the acid or base, depending on what you use, that the concentration was unknown. You can use the known concentration after the whole titration process to find the unknown. Okay, so during titration, there is a change in pH of the acid, or change in pH as the acid is added to the alkali. When the acid is added to the alkali, the pH of the alkali keeps reducing because the center point will be neutralization. Remember your pH scale. Center point should be neutralization. So if that base had a pH value of 14 before the acid was added, when you keep adding the acid, it will reduce to 13, 12, 11, 10, so on, down. If it reaches 7, with the help of that your indicator which is inside it, the color should change and tell you it's okay, it's now neutral. You understand? But the change in that pH depends on the strength of the acid and the alkali used. So if you're using a strong acid and a weak alkali, the pH will not change rapidly, to change slowly, because a weak base, a weak alkali is used. So you have to keep adding. But if a strong base is used against a weak acid, you will not add much of the base before neutralization takes place. But when it's practical, you will understand better. So you can now go to that table that says strength of reactants, titration reaction, rapid change, and indicator used. Now, if you are titrating a strong acid against a strong base, that is a strong acid, example hydrochloric acid, against a strong base, example sodium hydroxide, then you can use any indicator. Any indicator means you can use methyl orange, you can use methyl red, you can use phenol red, you can use phenolphthalein, you can use any indicator. And if you're titrating a weak acid against a strong base, a weak acid, example ethanoic acid, remember organic acids are weak acids, against a strong base like sodium hydroxide, please use phenolphthalein. Use phenolphthalein as the indicator in that reaction. But if you are titrating a strong acid against a weak base, strong acid, example hydrochloric acid, against a weak base like aqueous ammonia, then use methyl orange. You understand? Most times in the labs we use strong acids against strong base, so we can use any indicator. I personally prefer methyl orange. Alright, now think about this. Listen, if you are cooking soup, I don't know why I'm so much particular about this soup when I can't really cook it. Alright, so if you're cooking soup, let's say okazi, and then you've added your Maggi, seasoning and all those spices, you've added everything and you tasted it, and you discover that you need a little amount of salt to make everything balance. And then by the time you took the bottle of the salt or whatever container you use for salt, you took it directly over the pots and wanted to slash a little into the pots, and then the whole you slashed more than you should into the pot, what happens? You've condemned the whole soup, right? Because the taste becomes salty, right? Good. Now, in experiments, there is something we call buffer solutions. Now, if you mistakenly spill an acid or a base into a solution, maybe that solution was already neutral. Let's say it's neutral already, has 7, and you mistakenly spill in additional acid, small amounts of acid, and remember, if that was your soup, the salt will spoil the whole thing for you. But in buffer solutions, that small amount of acids may not change the pH of that solution, but that's only if it was a buffer solution. Okay, so I don't know if you have seen worm, normal worm, those ones that crawl on the ground, go to cold places. Now, if you pour a little amount of salt on worm, what happens? It starts shrinking, as if you shouted Jesus to winch. You understand? So if you pour a little amount of salt on a worm, it dries its blood. That worm eventually dies. But especially babies can lick a lot of salt and nothing happens to them. You understand? Now, the human body have what we call buffers in them, so that if we accidentally take in some dangerous things into our body, it may not lead to death. I'm not saying you should go and drink acid. It will burn you. Maybe by the time a solution is found, part of your body is already burnt. So don't try that. But I'm saying that in human beings, we have buffers in us, so that if there is a little change in pH in our system, it shouldn't affect the human body because of the presence of these buffers. So remember, buffers don't change in pH. The pH of buffer solutions don't change when little amounts of acids or bases or alkalis are added to them. Now, in the hospital, medical doctors medical doctors, they use these buffers in administration. Now, the blood inside you has a pH of 7.4, and even a little change as 0.5 would be fatal, would cause a person to die, so to say, as fatal as that. So change in pH of blood can be very, 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 very fatal. So these injections that are injected, the medicines injected into the human blood, if they are not protected by buffers, they can come in and alter the pH of the blood, which even a little alteration can prove fatal. So these medicines are equipped with buffers, so that by the time it is injected into the human blood, it won't come in there and change the pH and alter the pH of the blood. Okay, so buffer solutions are as important as that. So a buffer solution consists of a weak acid or a weak base in the presence of one of its salts. So if we say ethanoic acid plus sodium ethanoate, what's the weak acid there? Ethanoic acid, because it's an organic acid, it's natural. And aqueous ammonia plus ammonium chloride, what's the salt there? Ammonium chloride. So you see, we're already talking about salts. So we'll stop there for today. Remember, we are still discussing acid, base, and salt as our broad topic. We discussed acid in our last class, and today we've discussed base, that's alkali, and the reaction between acid and base. Next class we'll discuss salts to complete that topic, acid, base, and salt. Now, you've listened to all these teachings. If you have any question, drop them on that group and wait for your answer. And write the answers I give you, because I'm not there face to face with you. But you can write everything. There is no harm in writing. In fact, it will help you. And you can keep this record and listen to it over and over again until you understand. Also, on Sunday, I will drop the notes for next week. Sunday, by the grace of God, if Christ tarries, I will drop a note on the group, the notes for next week on the group. So do well to come online on Sunday, get those notes and copy, so that by the time I'll be explaining this way, you'll be looking at your notes and you'll be seeing what I'm explaining. It's better than trying to figure out on the screen where that note is, you understand? So get it on Sunday, copy it ahead, so that by the time we are teaching, you're already looking at it, you understand better. Alright, I hope you enjoyed the lessons. Please practice them, go through them one by one again, and ask questions if you don't understand. And make sure you have a wonderful day. Goodbye. Okay, we've come to the last part of our topic, acid, base, and salt. We have treated acids, done justice to base, and here we are. I want to consider salts. Now, so many people have defined salts in different ways that may be complicating. Some say salt is an ionic compound that is composed of a cation and an anion. Others say a salt is a compound that contains cations apart from hydrogen plus, and anions apart from hydroxide as minus. But in such situations, Jesus would say, "But what do you say?" So we're going to define our own the way you will be expected to answer in WAEC. So let's go. A salt is the compound formed when all or parts of the ionizable hydrogen of an acid is replaced by metallic or ammonium ions. Remember when we handled acid, we said acids are substances which, when dissolved in water, right, they yield hydrogen ions as the only positive ions. And then on that basicity of an acid, we said that these acids can then be replaced by metallic ions. I used the example zinc metal. So it therefore means if a metal comes into that solution, then the metal would displace the hydrogen, send away hydrogen, I'm here, and then it will replace it, take its place. So let's take, for instance, we had HCl. That's what? Hydrochloric acid. HCl has only one H. Now, if we dissolve HCl in water, and then we have HCl. If we introduce zinc metal into it, one zinc metal, now zinc will come into the solution, pursue hydrogen, hydrogen will now be displaced as a gas to go out, and then zinc will take its place. It was HCl before, but since zinc has pursued hydrogen, it will now become zinc chloride. You understand? So a metal has displaced or replaced the hydrogen that was dissolved in water when acid was formed. So let's relate that to our definition of salts. I'll read it one more time. A salt is the compound formed when all or parts of the ionizable hydrogen of an acid is replaced by metallic or ammonium ions. I hope you understand that well. Now, as we go ahead, as we discuss the types of salts, you understand better. So, we're going to be considering 5 main types of salts. 5 main types of salts. Number 1, normal salts. Normal salts. Now, the salt you use at home, the salt you use for cooking, some people consume it directly or raw. Now, those salts can be classified under normal salts. Reason being that it does not contain does not contain acidic properties, also does not contain basic properties, so it's safe for consumption. Now, a normal salt has neither hydrogen H nor hydroxide OH. Now, whenever we say hydrogen, you think of an acid, and when we say hydroxide, you think of a base, right? Good. So if I say a substance contains H plus ions, that's hydrogen ions, you should already know that's an acid. Or I say a substance contains OH ions, you should already know that's a base, that's an alkali. But what if I tell you that a substance does not contain H ions, does not contain OH ions? Then you should be thinking of a neutral substance, right? A substance which is not acidic, it's not basic, it's neutral. Now, normal salts fall under this kind of substances. It's neutral, doesn't contain acidic properties, does not contain basic properties. So, a normal salt has neither hydrogen nor hydroxide in its formula. Example, we say sodium chloride. That's the salt you consume at home. Sodium chloride, NaCl. In the formula, Na, that's sodium, Cl, which is chlorine, combines together to be called sodium chloride. Did you see any H? No. Did you see any OH? No. So, sodium chloride is a normal salt. It's a normal salt, so it's neutral. It's safe for consumption. Okay, let's move on. They are formed when all the replaceable hydrogen ions in the acid have been completely replaced by metallic ions. Remember, when acids are dissolved in water, the hydrogen ions ionize. Now, and we said metallic ions can come in and replace those hydrogen ions. Displace and replace them. Displace is pursue, replace is take that place. So you can use this place to mean both. Now, let's say we had 2H. Let's say H2. Okay, let's say HCl. We had HCl. Let's use H2SO4, sulfuric acid. We have H2SO4, and we dissolve it in water. How many hydrogen ions do you find there? 2, at least 2, right? H2, good. Now, the H2 was ionized and in the water. So two molecules or 2 hydrogen atoms are present, ions are present in the solution. Now, if we introduce a metal, but we just introduce one metallic ion into the solution, that metallic ion will go in and displace just one hydrogen ion, because it's not enough to displace the 2 hydrogen ions there. And because it has displaced only one hydrogen ion, takes its place, what is found inside the solution? Hydrogen is still there. Hydrogen is still there. Take note, hydrogen is still there. Now, since hydrogen is still there, the salts formed will still contain acidic properties. Do you understand? Because the the replaceable hydrogen ions were not completely replaced. You get the gist? They were not completely replaced. So when this happens, you get a type of salt we are going to discuss as we are going. But for normal salts, the replaceable hydrogen ions are completely replaced. So if, for example, we say HCl goes into the water and only one H is formed, and then we put in sodium, Na, just one, and it goes in, takes the place of just one hydrogen. There's no more hydrogen in the solution, so sodium takes the place. It now becomes sodium chloride, as a normal salt we know. So all the hydrogen there has been replaced. So that's when normal salts are formed. I hope you understand. So normal salts are neutral to litmus because there is no hydrogen present in it. It will not turn blue litmus red, since as acids turn blue litmus red, and since there is no hydroxide present in it, it will not turn red litmus blue, since bases and alkalis turn red litmus blue. So if you put in a red litmus paper into a normal salt, the color should remain red. And if you put in a blue litmus paper into a normal salt, the results, the paper should come out blue. No change, no effect on litmus paper. Now we go to the second type of salts, acid salts. Acid salts. Acid salts are formed as a result of the reaction between a strong acid and a weak base. A strong acid and a weak base. Now remember, we said acids can either be strong acids or they are weak acids. They are strong acids if they are prepared in the laboratory, if they are artificial acids, or inorganic acids, yes. We said organic acids, which are natural acids, are weak acids, like citric acid, ethanoic acid. Citric acid is found in fruits, unripe fruits, so that's a natural acid. So it's weak. If you eat it, it's not that harsh. You just receive a slap or sour test. It doesn't kill you, right? Good. Though a large amount can purge you and cause harm to your system, but it's not harsh, it's not strong to cause death, so to say. So weak acids are natural acids, organic acids, and then strong acids and inorganic acids. Now, when you are reacting a strong acid with a weak base, then the result will be a product that will have an acidic content in it, because acid was stronger than the base. Take, for instance, you mix 1 liter of water that contains 2 full packs of sugar. You mix that 1 liter of that kind of water with 1 liter of another water that contains just 1 teaspoonful of salt. They now become 2 liters of water solution, yes. But the solution will taste sweet. It will not taste salty, because the amount of salt dissolved in the other 1 liter was just 1 teaspoonful. But the amount of sugar dissolved in the other 1 liter was 2 packs of sugar. So, this product will taste like there is no salt in it. It's sugary. It's still going to be very sugary. So we can say the sugar, since it contained a lot of sugar, the 1 liter that contained a lot of sugar, we can call that the strong acid. And the 1 liter of water that contained only 1 teaspoonful of salt, we call that a weak base. Though they are still 1 liter, but if you taste this one, the concentration is low, and you taste the other one, the concentration is so high. So when you mix them together, the one that has high concentration overpowers the other one, so to say. So compare that to when we say acid salts are formed as a result of the reaction between a strong acid and a weak base. So the strong acid will overpower the weak base, and so the product will still have acidic properties in it, because it was so stronger than the base. Now, acid salts are formed when the replaceable hydrogen ions, listen, when the replaceable hydrogen ions in acids are only partially replaced by a metal. So if the hydrogen ions were partially replaced, it means some of the hydrogen ions are still present in that solution. Because they are still present, remember, since H is still present, then it still has acidic properties. So that's why we call that kind of salt produced an acid salt. Do you understand? Acid salt, because the hydrogen inside that solution was not completely replaced. And whenever you say hydrogen, you are talking about an acid. So the hydrogen was not completely replaced. Because of that, it still has acidic properties. So the salt that will come out will be an acid salt. So acid salts are formed when the replaceable hydrogen ions in acids are only partially replaced by a metal. This happens when there is an insufficient supply of metallic ions to replace all the replaceable hydrogen ions in the acid. Like I said, if you're putting in only one atom, one ion, one sodium ion into a solution that has two hydrogen ions, one sodium ion, so to say, will be able to only displace one hydrogen ion. The other one will still be left. Sodium is insufficient to replace all the hydrogen there. So what will be formed will have hydrogen still present in it. So since hydrogen is still present, an acid is still present in it. So the result is an acid salt. Now, take note of this. Remember when we did neutralization, we said an acid reacts with a base to form salt and water only. Remember I said during neutralization there are only two products you should expect: a salt and water. Now you call that process neutralization, where salt and water is formed. Now the kind of salts formed when acid and base react are these that we are explaining. So it can be a normal salt, it can be an acid salt that we are explaining now, it can be a basic salt, double salt, complex salt, and so on. So we are on acid salts now. Now let's continue. Acid salts are produced only by acids containing more than one replaceable hydrogen ion. I hope you understand that now. So if we dissolve HCl in liquid, in water, and sodium comes in, sodium sees only one H, you can replace it easily because it's just one. So for you to have acid salt, you have to have in the reaction acids that have more than one hydrogen, so that when the metal comes in, it will not be able to displace all the hydrogen because it's more than one. So an acid salts are produced only by acids containing more than one replaceable hydrogen ion. Therefore, acids with two replaceable hydrogen ions can form only one acid salt. You understand? Because one of the other hydrogen will be displaced, only one hydrogen left. So while acids with three replaceable hydrogen ions can form two acid salts. Do you understand? If sodium is just one, comes into a solution where the hydrogen ions were three, it will displace one. How many remaining? Two. Okay. So two acid salts can be formed. But if it comes into a solution where you have two hydrogen ions and the metal is just one, displaces one is left. Okay, one acid salt is formed. So understand that statement. Acids with two replaceable hydrogen ions can form only one acid salt, while acids with three replaceable hydrogen ions can form two different acid salts. So you see the equation in your notes. H2SO4, that's sulfuric acid, combines with KOH, potassium hydroxide, to produce KHSO4. Look at that KHSO4, that's the salt. KHSO4 still has H in it, isn't it? It still has H in it. So since it has H in it, that salt is an acid salt. So we can say potassium hydrogen sulfate is an acid salt. Okay, so sulfuric acid combined with potassium hydroxide to produce potassium hydrogen sulfate salt plus water. So you see that acid plus base reacted to form salt and water. Okay, an acid salt contains hydrogen ions. That's a summary. Since we said acid salts can only be formed when you have acids containing more than one replaceable hydrogen ion. It means since there are still acid or hydrogen ions in the solution, then an acid salt contains hydrogen ions. That's an easy way to identify acid salt in equations. Like we said, normal salt, NaCl. Okay, the easiest way to know normal salt is when you see in the equation there is no hydrogen, there is no hydroxide. Okay, then it has to be a normal salt. Then in acid salts, how do you easily know an acid salt? When you see in the formula, you see hydrogen ions present in the formula. Okay, this acidic, because hydrogen signifies acid. So an acid salt contains hydrogen ions and has acidic properties. Once it contains hydrogen ions, it's going to have acidic properties. Acidic properties like, it will turn blue litmus red, just like an acid will turn blue litmus red. So examples of acid salts include NaHSO4, sodium hydrogen sulfate, or you easily say sodium bisulfate, and NaHCO3, sodium bicarbonate, or you say sodium hydrogen carbonate, NH4 ammonium, and NaH2PO2, etc. Those are all acid salts. We have many and many more of them, but take note, in all of their formulas you see hydrogen in them. NaHSO4, the other one NaHCO3, the other one NH4, the other one NaH2PO2. So acid salts have hydrogen present in them. Alright, so we move to the third type of salts, basic salts. So already you should expect that basic salt should have basic properties and should be the opposite of acid salts. So let's go. Acid salts or basic salts are formed as a result of the reaction between a weak acid and a strong base. Remember, acid salts are formed as a result of the reaction between a strong acid and weak base. But now, since it was strong acid and weak base, the stronger one stood out and it became an acid salt. But now, is a weak acid and strong base. The stronger one will stand out, so the result will be a basic salt. So basic salts are formed as a result of the reaction between a weak acid and a strong base. They occur when there is an insufficient supply of acid, which is needed for the complete neutralization of the base. Remember, when there was not enough metal to replace the hydrogen ions, that's why hydrogen was still present in the solution, and we call the salt formed acid salt because there's still hydrogen. But now there is no enough acid. The base, the metal that is introduced into the acid solution, maybe we say HCl, was dissolved in the water, and then you introduce a base that has that's more than one ion, say Na2 sodium, 2 sodium, and let's discuss it as with normal terms. Now you put 2 sodium into a solution that contains 1 hydrogen. Good. If you do that, and sodium is a metal, it will go in there and replace the hydrogen. But since it's 2 sodiums, let's say that, and it goes into that solution, and how many hydrogen ions will it replace? Well, just the one that is present in the solution. So it means 2 sodium to replace 1 hydrogen. A sodium will still be left in the solution because it doesn't see any hydrogen to replace. One has replaced the other one. The other one is still present. It's looking for what to replace, but no more hydrogen. So there is now insufficient supply of hydrogen ion, insufficient supply of acid, which is needed for the complete neutralization of the base. Now, basic salts contain hydroxide ions because that sodium, being a base, a metal, went in there and was too much, so it was left behind. It will contain basic properties. Since the base, it will have OH, hydroxide ions still present, just like acid still had, since acid was still there. Now, so since it has basic properties, since it has hydroxide ions, it will have basic properties. And basic properties like to turn red litmus blue, since a base can turn red litmus paper blue. Good. All right. Examples of basic salts include MgOHCl. Look at your notes. We have CaOH2. We have CaOHCl. We have MgOHNO3, etc. And I added that alum is a basic salt. Now, what I really to take note of is that you see in all the formulas, you have OH present in them. OH, say MgOH, say CaOH, say CaOH, say MgOH. So it means basic salts contain hydroxide ions. All right. The fourth type of salts, double salts. Double salts are salts which ionize to produce 3 different types of ions in solution. Now, the other 3 types of salts we were explaining, you discover that it has acid and base. It has hydrogen and OH. It's when the hydrogen is more than the OH and it becomes acid salt. When the OH is more than the H, then it becomes basic salt. But when they are normal, when they are neutral, it's a normal salt. But now in double salts, we form 3 types of ions. Not that there's another extra type of ion. You will understand that. Now, that's where the definitions others have been having, come to play here. You remember I said when we started that some people can define a salt as an ionic compound that contains a cation and an anion. Good. That's still a definition, since all these salts I mentioned will either contain acid, will contain H plus and OH minus. The proportion, the bigger proportions prove why they are acidic salts or basic salts or normal salts. But here in double salts, 2 positive ions are formed, so 2 positive charges are formed and the other negative. So 2 positively charged ion and 1 negatively charged ion are formed in double salt. So 2 plus 1, 3. So that's why we say they produce 3 different types of ions. 2 positively charged ion, the other 1 negatively charged ion. Like we have in hydrated double salts, KAlSO42 with 12 molecules of water. That's why it's hydrated. Hydrogen, water. So that's for double salts. Now the 5th type of salt, complex salts. Complex salts. Complex salts are formed by mixing together 2 simple salts. 2 simple salts. Example, if we mix tetraamine copper 2 ion, tetraamine copper 2 ion is prepared by mixing together copper 2 tetraoxosulfate 6 solution and ammonium hydroxide solution. So 2 simple salts are combined. 1 simple salt being copper 2 tetraoxosulfate 6 and the other one being ammonium hydroxide solution. Ammonium hydroxide. So if we combine those 2 together, we form a complex salt. So 2 simple salts can combine and form a complex salts. And those are the 5 types of salts we are going to define or classify or explain. Those are the main ones. Others are used when they are needed, but these ones will cover everything you need. All right. Now, if I say uses of salt, at least you will know one of them. since you use salt a lot in the house. So, uses of salts. Number one, they are used in the manufacture of industrial, agricultural, and consumer substances. Industrial substances, agricultural substances, and substances you can consume, like chlorine gas, industrial, fertilizer, agricultural, and laxatives. You use it a lot in your food materials and food, some sachet food and all those baking stuff. Now, number two, they are used as food preservatives. You use this now, you use it inside your food. And they are used as drying agents and antifreeze. You should know other uses that can be commonly said. It's used for salting of fish and food preservatives, and it gives good taste to food when added. So that's just the uses of salts. Now, how do you prepare salts? Soluble salts. How do you prepare salts in the laboratory? By the action of dilute acid on a metal. Remember, when acids are diluted, that's a dilute acid that's dissolved in water, then a metal can come in and displace the hydrogen present there, and then a salt is formed and water. So one is by the action of dilute acid on a metal. You see the examples there: zinc plus 2HCl will form zinc chloride plus water. So as base and acid forms salt and water, and Mg plus H2SO4 forms MgSO4 and water. Now, another way of preparing salts: by neutralization of an alkali by an acid. Remember our neutralization reaction? When acid reacts with bases, they form salt and water, and we call that neutralization. So that process forms salt actually. So that salt form, that's a way of producing or preparing salt, by neutralization of an alkali, that's base, by an acid. Now that's what we see: sodium hydroxide plus HCl produces NaCl plus water. Now, number three, by the action of a dilute acid on an insoluble base. Remember we said bases that are soluble in water, that can dissolve in water, are called alkali. So the other ones that cannot dissolve in water are the ones we call insoluble base, cannot dissolve. So if a dilute acid is reacted with an insoluble base, a salt will still be formed, since acid and base form salt and water. Like we have 2HCl plus MgO produces MgCl2. MgCl2 is a salt and water. And then number four, by the action of a dilute acid on trioxocarbonate 4. Alright, now if we have salt in a solution, remember what a solution is. I'll remind you again that solute plus solvent equals solution. Like what you want to dissolve in water is a solute, like your sugar. Solvent is what you use to dissolve it, like your water. So what you have is a sugar solution. So you are saying solution already. Sugar dissolved in water is a sugar solution. So sugar is a solute. What can dissolve in water is a solute. Solvent is what dissolves the solute, and the result is a solution. So solute plus solvent equals solution. Now, if salt was your solute and water is your solvent, and then a salt solution is formed, now how can you get back your salt? Supposing someone says, oh well, I need that salt back. That salt you dissolved in water, I need it back in its fresh form, the way you put it back. You put it inside the water. I need it back. I want to use it. Okay, it can happen. Now, recovering soluble salts from solution. Of course, if it's not soluble, then it will not be found in solution. So if it's not soluble, if it doesn't dissolve in water, simply just drain off the water and pick back your salts, because it did not dissolve. But the ones that are dissolved and you cannot find any small crystal of the salts in the solution, then how do you recover those ones? That's what we are considering now. Now, you can use two methods to recover soluble salts from a solution. Number one, heating to dryness. Heat, applying heat until the solution dries. Now, this can only happen when the salt you want to recover can withstand heat. Of course, if it cannot withstand heat, then it will melt. It will not form that crystals again. So it has to be salt that can withstand heat. Now, so the salt is put in an evaporating dish, simply a pot, and heated slowly to dryness. When the water dries, the salt will crystallize back. So the solid salt will now form back since the water in it is dried off, and then you get your salts. Now, most of the soluble salts, most of the chlorides, except you're talking about zinc and iron chlorides, most of other chlorides are recovered that way by heating the solution so the water dries off, and then you get back your solid crystalline salt. Now, the second method is crystallization. Now, this method is used when the salts can decompose or be destroyed rather than withstand heat. So if the salts can decompose, can be destroyed, then you can recover it from or using crystallization method. Now, how does this happen? The solution is first boiled. And when it's boiled, so that the amount of water in the solution will reduce more. Let it just reduce. Now, after the amount of water has been reduced, then bring it down and allow it to cool, the solution to cool down. Now, when you get to SS2, you will learn something called solubility. That the amount of substances dissolved in a particular solvent depends on the amount of that particle in there. Now, if a solution, if a solvent like water was used, then boil it. When you boil it, the solution will reduce, the water will reduce in the solution, and then bring it down, it cools. Now, crystals of the salt will begin to appear in the solution. The water is reduced, so the salt will form back, start forming. Now, when that happens, you can, to speed up the process, add a speck, just a little of that, the type of salt, this salt you want to regain, a little of that type of salt. Just add a little to that solution that is cooling, and then boom, everything will crystallize back, not magically, to help the process speed up and then crystallize. And some people can use the method of scratching the inside of the container with a glass rod. Not adding the extra salt now, extra small salt. Now scratching the bottom of the container with the solution is with a glass rod can also speed up the crystallization process. So soluble salts can be recovered from a solution using these two methods. Also remember, when we were doing separation techniques, crystallization was part of it. Now you should understand crystallization better, and even when you get to SS2, you'll be taught solubility, then you will understand crystallization even better. All right, now how do we prepare in the laboratory insoluble salts that cannot be dissolved in water, cannot dissolve in water? Now, number one, double decomposition. Now this is just adding or combining two soluble compounds, but one of the compound must contain the metallic radical and the other should contain the acidic radical. Remember, acid will replace, or metals will displace the hydrogen. So one of the soluble compound should contain the metallic radical, the charge, and then the other should contain the acidic radical. So when you mix these two soluble compounds together, you will form two products: an insoluble salt and a soluble product, a soluble substance. So take for instance, AgNO3 is soluble, as can dissolve in water. You mix it with NaCl, your common salt, which can also dissolve in water. Now if you mix that together, two products will be formed, AgCl. When you get to SS2, you will learn double decomposition method of reactions. You see why it's formed AgCl. Ag simply changed neighbor. Ag changed its base, its NO, and gave it to Na. So and took the neighbor of Na, that's Cl, clings to itself. So they simply change neighbors. You understand that when you get to SS2 and you are learning double decomposition types of reactions. So an insoluble salt is formed, AgCl, and a corresponding soluble substance, NaNO3. So that's one way of preparing insoluble salts. Another one is combination of constituent elements. This seems to be the simplest, when we always discuss it, we say just like you cook your soup. Now you add this and add this and add this and you get what you want. So if you want to get an insoluble salt, simply add a different component that make them up. Like we add iron, Fe, with sulfur, and we get FeS. You understand? We add 2Fe with 3Cl. We have 2FeCl3. You understand? That was simple combination. Just add. Combination means addition. Addition of the constituent elements can give you what you want. In this case, our insoluble salts. Okay, so remember we said solute plus solvents gives solution. Now, if your solute is salt and your solvent is water, then you're going to have a salt solution, right? Good. So we're going to discuss that under hydrolysis of salts. Hydrolysis is the reaction of a salt with water to form a solution, which is either acidic or basic. So the solution can be an acidic solution, or it can be a basic or alkaline solution. But what is paramount is that that solution contains salt and water. Now, salts form from strong acids. Remember, salts form from strong acids. When they react with water, they form an acidic solution. Salts form from strong acids and weak bases. So acid salts, let's put it that way. Acid salts, when the type of salt you use as solute to mix with this to dissolve in the solvent is an acid salt, then what is going to be formed, the solution that is going to be formed is a salt solution, right? But it's going to be an acidic solution because it's an acid salt you used. Now, on the other hand, now if you're using a basic salt that has OH minus, so it was formed using strong base and weak acid in combination. So if you have a basic salt and you are reacting that salt with water, it's going to form a salt solution, right? But it's going to be a basic or alkaline solution because it has more of the stronger proportion of the base. It's a basic salt. So that happens, and we call that hydrolysis. Remember, hydrolysis is the reaction of salt with water to form solutions, and that solution can either be acidic solution or it can be basic. Now, that leads us to a very interesting subtopic, water of crystallization. Water of crystallization. Good. Now, many salts combine chemically with water to form hydrates. Hydrates. Remember the other time we said hydrated, and we mentioned the big name, hydrated. So, hydrates, when salts combine with water, they form hydrates. Now, water of crystallization is the definite amount of water which a substance combines with when it forms a salt from its aqueous solution. Remember, we said aqueous solution is a solution where water is the solvent, not oil, not any other kind of solvent, but water is the solvent. So when a solution forms and when a salt is formed from an aqueous solution, the amount of water that combined with that substance to form that salt is the water of crystallization. So all hydrated salts have a definite amount or number of water molecules associated with one formula mass of that hydrated salt. So when certain compounds are exposed to air, they either lose their water of crystallization, or they absorb moisture from their surroundings. So if they lose their water of crystallization, they shrink, they become drier than they were. But if they they dry off. But if they are absorbing, they dilute themselves, they liquefy. You understand? Good. Now, the first set of occurrences or phenomenon that happen under water of crystallization we're going to discuss is efflorescence. Efflorescence. Now, this is a phenomenon whereby crystalline salts, hydrated salts, lose parts or all of their water of crystallization when exposed to the atmosphere, thereby forming a lower dehydrated or anhydrous salt. Phenomenon whereby salts, hydrated salt, crystalline salts, lose parts. It may lose part of its water of crystallization, or it loses all of its water of crystallization when it is exposed to the atmosphere. And when that happens, it becomes dehydrated. It has lost its water of crystallization, so it loses the water and it becomes dehydrated. An example can be seen when copper 2 sulfate crystals are exposed to air. You see, they slowly lose their water of crystallization from its surface, and becomes a white layer of copper 2 sulfate. So it loses the water of crystallization and becomes dehydrated and hydrous. Alright, the second phenomenon is deliquescence. Deliquescence is the opposite of efflorescence. Deliquescence is when compounds absorb a large amount of water when they are exposed to the atmosphere. So you see, when they do that, they turn into solutions. So if it's absorbing moisture to itself, absorbing water to itself, then it will add that water it's absorbing to its own water. So the result will be, it will become more watery than it was, right? That's now we say that's turned into a solution. Example is sodium hydroxide, ammonium chloride, gold 2 chloride, sodium nitrate, calcium chloride, etc. Even your normal salts, you can try this at home. If you take a little of your sodium chloride, that's your salt in the kitchen, put it in a paper. Keep it, preferably a paper. Keep it on the paper. Take it outside. It may not be sunny. You don't even need a sunny day. Just take it outside where there is air, and then let air touch it. Before 10 minutes, you will see that you go back to that salt, you see traces of water in the salt. it's almost like you poured water, a little amount of water on it. But if it doesn't show really well, just shift the salt from where it was, and you see the bottom, the paper will show signs of water. You understand? That's why I said preferable you put it on paper. Now what happened? That's your salt absorbed moisture from the air around it into itself, and now instead of becoming dry, if it were a fluorescent, it's now becoming more watery than it was at the beginning. So if you keep it there for long, you see at a point you will not see seeds, those crystals, those solids anymore. Those solids are what we call crystals. You don't see them anymore. They become liquid, so they have turned into solution. So when that happens, you say, oh, deliquescence has occurred. Now the third phenomenon is hygroscopy. Now a hygroscopic substance is that substance that readily attracts water from its environment, just like the deliquescent substance, though or through either absorption or adsorption. Remember, absorption, 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 or adsorption, adsorption. Now absorption is like you put your foam into water, a little foam into water. The foam sucks up water, drags water into itself. That's absorption. That's if the salt now drags water into itself from the environment. Good. That's like the deliquescence. But there's another way it can do that. It's adsorption is for something to adhere, stick to a surface. Like if you carry if your hand is, if you pour a little gum on your hand, if you pour gum on your hand, say Top Bond or any kind of liquid gum, and then you go close to particles of paper, you go too close to paper and touch paper, the paper will stick to your hand, right? Good. So we can say the paper adheres to your hand because of the glue. Now water when some substances, when exposed to the environment, water can now stick to their body. That's adsorption. So when substances attract water from the environment through these two ways, either it absorbs the water or it adsorbs, water just sticks to its body, then hygroscopy took place. So if the hygroscopic substance is a solid, you see, it does not absorb moisture enough to turn into solution. For you to turn a solid into solution, you have to, there have to be pores in the solid so that water can go into it. So if this substance is a solid, it will not be able to absorb enough moisture for it to turn into solution, just become watery. Instead, you see, it will become sticky. You understand? It will become sticky, like your glue. It becomes sticky or moist. Good. But if it was a liquid, then it will absorb water, just like with the deliquescence, to absorb the water enough and then dilute itself and become a solution. In fact, it can dilute itself up to 3 times the amount, the volume of the original water it had. So it becomes 3 times liquefied. So that one is if it was a liquid. But if it was a solid and it absorbs water from the environment, it becomes sticky, not solution. Now it doesn't become liquid. All right, that is under hygroscopy. Now we use these hygroscopic substances a lot in drying. Used as drying agent, since it can absorb water to itself, and if it was solid, it will become sticky and you can still remove it out. But if it's liquid and it's absorbed water, the liquid will now go back again and soak up you understand? So it has, if it's solid, we can now, if it attracts water to itself and becomes sticky, we can now remove the sticky solids, and it has help to withdraw the water from dry what you wanted to dry. So examples are quicklime, copper 2 oxide, sodium trioxynitrate 5, and others. Okay, now we get to the last subtopic for salts. In fact, the last subtopic for acid, base, and salt. Now, most acids, bases, and salts are electrolytes. You know what electrolytes are? No, I don't think so. But in SS2 you will understand what electrolytes are, but I'll just define it simply. Electrolytes are substances that can conduct electricity. Substances that are in liquid form that can conduct electricity. So most acids and bases and salts can conduct electricity when they are in liquid form, molten form, melted. So they tend to exist in solution as ions, which are carriers of electricity, because ions carry electricity. Negative ions, electrons, and the positive ions. And not all electrolytes, however, can conduct electricity to the same extent. What are we trying to say? That not all electrolytes can conduct electricity the same way. Some can conduct electricity to a particular extent, some can conduct electricity better than the other, and so on. So we discuss this under conductance of acids, bases, and salts. How much can acids conduct electricity? How much can a base conduct electricity? Then how much can a salt conduct electricity? So the ability, the conductivity of acids, base, and salts. Now, generally, the conductivity of an acid or base depends on the amount of ions present and their mobilities. Mobilities, if they are moving or not. If they are mobile, if they are moving. The particles of solids are not mobile, they are not moving, they are static, they stay in one place because they are in solid form. They are not moving. Remember when we studied that particulate nature of matter. So because the ions in solids are not moving, then the ions present in that solid will also not be moving. So since it's not moving, it's not mobile, then it cannot conduct electricity. So that's why it has to be in solution. Now, so the conductivity, how much this acid or base or salt conducts electricity, depends on how many ions are present in that solution and how many are moving, how mobile are there. Good. So a strong acid or a base, a strong acid or strong base, strongly conducts electricity, because a strong acid has hydrogen ions present in them. So you see the ions are present and they are moving because in solution, it is in liquid form, not solid. So a strong acid or a strong base conducts electricity due to their large number of ions, while a weak acid or base only conducts electricity weakly because it contains a few ions. So you understand that. Now, what I really want you to put into your memory is that the conductivity of an acid or base depends on two things. One, the amount of ions present in them, and two, how mobile, are they moving, their mobility. If you know that, then you understand the conductance of acids, bases, and salts.